בסדר? נהדר. אוקיי, אז בעצם ההרצאה הזאת, אני נעבור לאנגלית. This presentation is going to go through the consumer rebalance protocol in Kafka. And I'm going to do a very quick intro to Kafka with the assumptions that most of you know it, and then kind of just to introduce how the consumers work. And then I'm going to talk about the design, how we thought about the design, because you'll see the protocol is kind of weird and is kind of maybe slightly more generic than if you'd think, how would I do it myself? This is probably, our implementation is not what you would come up with, let's put it that way, but we had some unique requirements and I'm going to talk you through that. And then I'm going to dive into the internals of the protocol. And then I'm going to show you how to use the same protocol to do things that have absolutely nothing to do with consumers and possibly even nothing to do with Kafka, just as a general resource management protocol that is available for different things. Some may say that it's easier to use than Zookeeper. I would definitely say that it's easier to use than Zookeeper. Okay, me, I work on Kafka stuff and I've been doing it for a while now. תודה. זה פשוט לא עובד? כלום. אוקיי. אז כעיקרון, כשמדברים על קפקא, Apache Kafka, יש בו כל מיני רכיבים. יש בו את ה-producers consumers, יש לנו קונקטורים, יש לנו stream processing. פחות או יותר כולם משתמשים, הסיבה שכולם חלק מה-Apache Kafka זה שכולם עובדים עם אותם פרוטוקולים של Apache Kafka. ואנחנו, בעצם, אני מדברת על הפרוטוקול, אני אדגים איך כולם עובדים באותה צורה. Next. אוקיי, קפקא. בקפקא הרעיון הכללי הוא שיש לנו producers, הם מפבלישים messages. Messages go into topics. Topics are just a logical construct of something that things may be interested to. So consumers subscribe to topics, they get all the messages in a topic. In order to scale topics, we cut them apart into partitions. If you are familiar with any other database, you will call them shards. And the idea is that each one of those shards is replicated into multiple brokers. This is what gives us high availability. So we have lots of partitions to provide scale and replicas for each partition to provide high availability. Next. Okay, the ways that replication work. Right now, it's a leader-follower type of replication, which means that producers always write into the leader replica. Consumers always read from the leader replica. The follower replicas have one job, and this is to keep up with the data getting written to the leader, and they should be available for failover in case something happens to the broker that the leader is on. So that, just as an interesting tidbit, we now have a proposal going in the Kafka community that proposes to allow consumers to read from replicas, which is going to be huge because if consumers can read from replicas, it means that you can suddenly spread a cluster across a larger geographical area and read from the closest local replica, which is going to be absolutely amazing. If you're, say, on AWS and you run Kafka across 3 availability zones, and you notice that the cost of traffic between availability zone is kind of high, if you can consume from the nearest replica, you are going to cut your traffic costs by a pretty significant amount. How do we know? Confluent is running Confluent Cloud. Kafka is a service. In high availability mode, we're running it across multiple availability zones, and we are the ones paying for traffic and not our customers. So we are highly motivated to solve this problem in the near term. So that has nothing to do with the rest of my talk. It's just a cool bit. Next. Okay, as I said, replica fails. We're basically doing electing a follower as the new leader. Next. Cool. Okay. Consumers. So the idea, the basic idea in Kafka consumers is that consumers keep track of where they each message in a partition has a number called offset. Consumers start reading usually at the beginning, offset 0, and they progress along just reading, okay, offset 0, and then they call Kafka and say, give me more data. Now they're reading message number 1, message number 2, and so on and so forth. Next. This is going to be very difficult. We have very dynamic slides. Okay, so every time you get to a safe point, which is defined by the developer usually, you commit your offsets. Meaning, Kafka, please remember that I've read messages until message 6. So if I crash and I come back up, the next message that I read will be message 7, because Kafka remembers that I read until message 6. How does Kafka remember that? It gets written to the consumer offset topic. So we have a topic, and we produce a message to the topic. I am consumer X, I'm reading from partition Y, and the latest event that I've read is number, I'm reading from partition 0, the latest event is 7, from partition 1, the latest event is 4, and if I crash and come back up, I can just read it and say, oh, that's my last location. Now you can have a lot of consumers, and they each have their own location, and they basically each commit with its own consumer group. So you can have many consumers reading data independently. Next. Okay, so consumer groups, since I just mentioned them, basically if you have a consumer instance, it will read events from, it will subscribe to a topic, and it will start reading events from all the partitions in the topic. Next. If you have 2 of them, then they're going to divide, basically load balance. They're going to somehow talk to each other and say, I'm reading partitions 1 and 2, you're reading partitions 3 and 4, and just keep on working that way. This entire talk will be about how they do that. Next. Note that when the consumers commit offsets, all the consumers from the group write the offsets to the consumer offset topic, and they all write it to the same partition. And basically, you take the consumer group ID, you hash it, and you find out which partition you're writing to. This is important because when I come back up, if I have tons of consumer groups, I don't want to actually try to look through the offsets for every single consumer group. In Kafka, this allows me to just read a single partition. By default, Kafka has 50 partitions in the consumer offset topic, which allows you to really support a fairly large number of consumer groups. Next. Now, the consumer protocol also allows for failover. So remember, we had 2 consumers, each reading from 2 partitions. If one of them fails, it will get automatically detected, and the remaining consumer will start reading from all the partitions, meaning that by default we don't allow for orphan partitions that are not being processed by anyone. Again, this is something that we will explain in discussing detail exactly how it works. Next. Okay, and you can have as many consumers as you have partitions. If you try adding consumers more than you have partitions, we don't subdivide partitions. Instead, you will basically have kind of unemployed consumers that sit around doing nothing because there is no partitions for them to read. Next. That's unemployed consumer right there in the middle, no partitions for him. Next. Okay, so the rest of the presentation is how this consumer balancing works and what else can you do with the protocols that enables it. Note that the entire consumer protocol basically got rewritten again and again, and I think even again. So up until version 0.9, we stored everything that I'm going to talk about happens through Zookeeper. All the balancing, election, detecting when someone goes away, it all happened in Zookeeper. Somewhere in 2014, LinkedIn discovered that Zookeeper doesn't scale to the number of consumers and consumer groups that they have, and decided to rewrite the entire thing to work directly with Kafka, and that's when the first version of this protocol was invented. There was, as the first implementation of anything big, there was huge gaps in how we did it, and therefore it was rewritten between 0.8 and 0.8 and 0.8.2, rewritten again between 0.8.2 and 0.9, and rewritten again between 0.9 and 0.10. The version I'm going to talk about is the 0.10 version. We're still making minor tweaks, and I'll mention where we're tweaking stuff right now. Next. Okay, so I said I'm going to talk about the requirements. Why did in order to understand the protocol, you have to understand why we made it the way we made it. So let's go through what did we try to implement. The first requirement is basically what I just mentioned. If a consumer joins the consumer group, we want to automatically load balance, automatically assign partitions. If someone leaves the group or crashes, we want to, again, automatically detect it, automatically assign partitions. This was kind of the basic requirements. This is what Zookeeper already gave us, and we didn't want to give it up. So that was kind of the basic. Everyone understood this part. The controversial requirement was number 2. If you would probably implement it yourself, you would put all the logic in the broker. And that was kind of our first design iteration. If you look through if you Google for internals of Kafka consumer protocol, you will find a document in the Kafka wiki, 50-50 chance that you will find the older document that describes the implementation, where the broker itself basically kind of sees, oh, all those clients are connecting to the same consumer group, I'll give this partition, I'll give that this partition, and it kind of makes sense. The reason we decided to push the logic to the clients is almost a quirk of how organizations work. If I am a developer and I decide that I have a good idea of how to assign partitions to my clients, I need a certain kind of stickiness, I need a certain kind of logic. It's very easy for me to change the client because I'm the developer, I'm writing the client, I'll plug in a new jar and get to work. But if the logic is in the server, suppose that I write my amazing new logic, I have to give it to a sysadmin and tell him, please upgrade your Kafka server. Or even if the Kafka team himself, what if Jay Krebs has an amazing idea of how to better balance things, we have to wait until people upgrade their Kafka clusters. Usually our customers and organizations all over the world, even LinkedIn, are incredibly slow and conservative about upgrading the brokers because just the risk involved. Very, very active about upgrading the clients. Putting the logic in the clients allows us to be much more flexible and to just innovate faster on the partition assignment. And this turned out to be a good idea. We keep adding new partition assignment methods to Kafka on a very, very regular basis. I'd say that pretty much every release has either a new protocol or an improvement on an existing strategy. So that was a huge debate. We had to redo tons of work, but I think it was a good one. And then requirements 3 or 4 arrived from LinkedIn. Basically, their largest consumer group turned out to be somewhere in the 500 consumers in a single group. This is Mirror Maker. They have a huge cluster that they need to replicate from one side of the continent to the other. And then I think they mentioned having something like 50,000 consumer groups on a single cluster. So we needed to support at least those numbers and possibly give them some room for growth. So we were very sensitive on just how to support those large numbers. It turns out that we weren't quite good enough. Our largest clients, when they try to, for example, commit offsets from a large consumer group, sometimes run into the message size limits. So we're still working on improvements there as well. And then the last one, if the brokers are responsible for the assignment, it's usually a single broker and consistency is not an issue. If a client group has to agree on assignment, we have to make sure it's consistent. It can't be that we have 5 consumers in the group, I think I'm responsible for partition 1, he thinks he's also responsible for partition 1, and none of us are responsible for partition 2. We have to come up with a coherent strategy, so we had to take care of consistency. So let's now dive into the protocol and see how we did all of those things. Okay, so how does the protocol work at like the highest level? We need to support few operations. We need to allow a client to join the group and get an assignment, presumably. We need to do some kind of resource assignment, and that's where we ended up with something quite generic. Normally, the resource is a partition, but I'll show you 2 examples where the resource is something completely different. And then we have to maintain group membership. We need to detect when clients crash, right? Which means that we also need the clients to have some kind of a keep alive to say, hey, I'm still around, don't take my partitions away, please, every once in a while. And because we don't want to just rely on crash detection, we also need to allow clients to say, hey, I'm leaving the group, please reassign my partitions and give them away to someone else. Next. Okay, so we ended up with what ended up incredibly confusing. It's a multi-layered protocol. It has 3 layers, and each one of them is called protocol at some point in our code base, which makes reading our code base and reading the Java docs way more confusing than it otherwise would be. So let's take it from the top down. We have what we call the Kafka group protocol, and this is the part that's responsible for the group membership. It supports the operations of join group, synchronize group, leave group. I'll talk to you about all those operations. And that's just how do I manage who is a member of the group. Now that I have a group established, the group members themselves have to talk to each other and agree on who is responsible for which resources. The language in which they do it, what is a resource and how is it assigned, is also called a protocol. And we call that in some places a sub-protocol or just a protocol, just to make things quite confusing. And then there is also, once we agree on what is a resource and what is the language that describes the resource assignment, there is also the logic for assigning the resources and some metadata involved in making good decisions around it. And this is called the basically user data or metadata, and we also call it a protocol in quite a few places. So yeah, on behalf of Kafka developers, I apologize. We didn't notice it until it was too late. So anyway, I'll try to explain which layer we're talking about as I explain everything. Okay, so how do we use the protocol? So the big thing is the consumer group membership. That will be most of the talk today. And then we also use it in there is 3 products that I know of that use the protocol in slightly different ways. Kafka Connect uses the protocol to do the task assignment. Basically, Kafka Connect is basically what gets the parts of Kafka that connects to external databases and gets data from them or writes data to a database. We have tasks. Basically, you're responsible for reading this file and you're responsible for writing to that database. We use the protocol to assign the tasks to specific Connect workers, and I'll talk about that. Kafka Streams, if you're familiar with it, this is the stream processing part of Apache Kafka. It uses the protocol to also assign tasks to specific machines that do Kafka Streams. And then Schema Registry, if you're familiar with that, I'll talk about it a bit. It has a high availability mode in which it requires leader election. It used to use Zookeeper for leader election, but now we have Confluent Cloud. We don't allow anyone to connect to Zookeeper directly. We needed another solution for leader election. And hey, we had this handy rebalancing protocol available. So we used, and as I said, we like it way better than Zookeeper anyway, so we used that for leader election. Probably the simplest example, and immediately once I'm done talking about how we assign partitions, I'm going to start talking about how to do leader election. And I think leader election is kind of a common problem. We all have to do leader election every once in a while, so you'll enjoy that. Was that a hint? Okay, so the things we're talking about. We're going to have consumers that are going to be part of a consumer group. We have all the brokers. A component inside the broker is a coordinator. Every broker has a coordinator that is responsible for the coordination of one or more of the consumer groups, ideally about a fair share of the consumer group. And the first thing that a consumer has to do is find the coordinator. So let's talk about how that works. Next. Okay, so the first thing the first part of the protocol, I'm a new consumer, I come up, first thing to do, first order of business, find my coordinator. I cannot join a group until I know who is the coordinator. Next. Okay, so I basically, as you know, when you configure a Kafka consumer, you configure a list of 1 or more, usually 3 bootstrap servers. We connect to random one of those bootstrap servers and say, hey, I'm trying to join consumer group X. Who is my coordinator? The broker takes X, hashes it, divides it by the number of partitions in the consumer offset topic, which is usually 50, and then it comes up with a partition number. It looks for the current leader of that partition, That's what gives the coordinator high availability. And the broker that is the current leader of your consumer offset partition is your coordinator. And that's the endpoint that comes back. It basically tells you connect to broker X. Yes?
Is that for each consumer is a different process? Each one of them has the same consumer group?
Yes, exactly. We're talking about multiple consumers that are all part of the same group, so they divide the partitions between them.
And they are managed in the same process?
No.
So they can be like Java post each one of them, and they get a different partition with the same group.
Exactly. Repeat the question. Yes, okay. The question was whether the consumers all run in the same JVM or different JVMs. And the answer is they run on different JVMs, usually totally different hosts. This is basically our scale-in, scale-out mechanism. Yes?
If you repartition the topic that handles the metadata, so how do you know where is the right partition? Who is the broker?
I'll talk about repartitioning in about 10 slides. Okay, so we found our coordinator. I think the interesting bit here is that the metadata, we use the consumer offset topic to find the coordinator, even if we are not using consumers at all. Even when it's like schema register doing leader election and it has absolutely nothing to do with partitions, there will be no offsets involved whatsoever, we still use it because it's always going to be there and it's a handy way to assign a coordinator. So we found the coordinator. Next. After oh yeah.
How about high availability here? As we say, I can connect only if my leader, so leader of my partition is down.
Yes, fantastic question. So what if the leader for my partition is down? Well, we mentioned that each partition has 3 replicas. If the leader is down, Kafka, regardless, is going to do a leader election and find the new leader for that partition, and therefore you will have a new coordinator. In that case, and I'll talk about it in a second, everyone will just reconnect to the new, will re-execute the find coordinator and will reconnect to a new coordinator. Okay, so once we found the coordinator, we are going to join the group. So how do we join a group? Basically, every consumer who wants to join the group sends a join group request that involves the group ID. So I'm joining group X. It has a member ID, but the first time I'm doing it, my member ID is going to be null. So because I don't know what is my ID yet, I'm going to get the ID as part of the response. I'm sending the fact that I'm joining the consumer group. That's the part with the sub protocol. I'm joining a consumer group and not a Kafka Streams group and not a Kafka Connect group and not a schema register group. And you use the fact that I'm using the joining consumer group to interpret the rest of the data that I'm sending, which will be, here is the list of the assignment protocols that I'm interested in using, range assignment, sticky assignment, one of those, and those are the topics that I'm interested in. Here is the list of topics that I want to subscribe to. And everyone sends that. Now you may wonder, like I'm starting a bunch of applications at the same time, more or less at the same time. How does it work? There is a bunch of timeouts involved. How long do we wait for others to join the group before we complete? If someone joins after the timeout, then basically we have to reassign everything again and do another balance. I'm not going to go into those, but there is a bunch of configurations around how much to wait. And then there is also information about generations. I joined the group, I got an assignment. Is the assignment still relevant or did things rebalance? Not going to go into those either. But give me one, it's complicated enough as is. So we all basically send our list of topics and our list of assignment protocols and who are we, etc. And the coordinator gets all of those. The first thing it does is elect a leader. The leader election algorithms of the coordinator is incredibly complex and subtle. We create a big linked list of all the consumers that joined, and we take the first one. When the first one dies, we take the second one. That's why it's a linked list. So we pick a leader, and at least it's fast. And then we send the leader back the list of all the members in the group, all their metadata, including which assignments each one of them is interested in, which topics, all this information is sent to the leader. Everyone else gets a member ID, the protocol that we'll all use, and I'll talk about how we select the protocol in a second, and who is the leader. So everyone knows who is the leader. They mostly use it to know that they are not the leader, because only the leader gets everything else. Okay, so every member basically gets to say, I don't just say, when I create a consumer, most people basically just say, I want to use round robin assignment, or I want to use range assignment, or I want to do sticky assignment. But you don't have to. You can send a list. And it took me a while to figure out why do we have a list and why do we have this complex way to select which assignment algorithm we're going to choose. And it turned out that the reason it's so complicated is to allow for no downtime upgrades of consumer group. Suppose that I changed my mind and I want to move from round robin to sticky. I don't have to take the entire consumer group down and bring it back up. I can do it on a rolling upgrade. And I'm going to show you how in a second. It's important. Please remember that, because every once in a while in a conference, someone tells me that they are very disappointed that they have, in order to change the rebalance, they have to take the entire consumer group down and bring it back up, and they cannot really afford the downtime, and nobody lets them do it. You don't have to do that. And the reasons that a lot of people think that you have to do it is because you wrote this amazing way to do rolling upgrades of consumer groups and forgot to document it. So again, my apologies. It was a very complicated piece of code, and we didn't remember everything all the time. So let's say that we start with everyone is doing round robin, and then they want to upgrade. Basically, one by one, I restart them and say, okay, actually, I still want to do round robin, but I'm also interested in sticky assignment. And now I have two consumers that are upgraded. They already know that they want to do sticky assignment. One of them is all the generation. The coordinator gets all those preferences, right? Everyone sends them their preferences when they join the group. Candidates for becoming the new agreed upon assignment. And remember, we have to agree on assignment because consistency is an important part of our protocol. We can only become a candidate for an assignment if everyone is interested in it. This one is not interested in sticky, so sticky is not a candidate. We have one candidate, everyone voted for it. We are all using round robin. Now, a day later, I've already also upgraded the last one. Next. Thank you. So now everyone knows that we want to do sticky, but they also know that we used to do round robin. We now have two candidates, but everyone wrote sticky first, which means that sticky gets the priority vote. So sticky now has 3 votes, and basically by the time we upgraded the last consumer, he does a join group, and suddenly everyone gets the message we are now doing a sticky assignment and not the old school round robin assignment. So this allows you to do rolling upgrade. Don't forget it. It will be very important for your career one day. Next. Okay, so remember, everyone joined the group. The coordinator selected the assignment for you. The coordinator sent the leader all the information. The leader selected the assignment for you. The next thing you do is that you need to know what partitions to read, right? The first join didn't do it for you. You have to do a sync group. So you send a join group, and then you immediately send a sync group. What does a sync group look like? Yep. The leader, when he does a sync group, sends, this is in the group. Here is my member ID. And this is the assignment. What is an assignment? Consumer 1 reads partitions 5 and 6. Consumer 2 reads partitions 3 and 4, etc. That's just a big hash map. That's an assignment for you. Everyone else who is not the leader just says, this is my member ID. I got the member ID in the last round. Coordinator stores the assignment. It is stored in the big consumer offset topic, and sends back each one of the members only his own assignment. So your consumer ID number 1, here's your partitions. Fairly straightforward. And at that point, everyone knows what partitions are assigned to. We can start reading data finally, if you think we're efficient, yeah, we're kind of not. That's why we try not to rebalance too often. It's a long process, it has all the timeouts, etc. Next. Okay, we have a consumer group, we know what to consume, everything is synchronized, we start reading data. Next. Now, as I said, we also need to maintain membership with the group. We have to keep telling the coordinators that we are still alive. Next. This is incredibly easy. We say, here's my member, I'm member 5 of consumer group X, and I'm still alive. And if all goes well, the coordinator will say, thank you, and basically send back in 0. We are very efficient that way. It's more interesting if sometimes it doesn't say okay. Next. And of course, if we want to go away in an organized way, we can also say bye-bye. Next. So we basically say, I'm member 5 of consumer group X, goodbye. And the coordinator now knows that it needs to do a rebalance, and we'll talk about it in a second. But the response is also very simple, bye-bye. Next. Okay, so we're almost done with the consumer group protocol. Only one thing. What does it mean when we actually have to rebalance? We detected that someone dies or someone said goodbye. We need to reassign stuff. How does that happen? Next. So that's kind of the big deal. So first of all, when do we rebalance? We rebalance when a member dies. We stop getting heartbeats. When someone leaves the group. But also, if, for example, we have new partitions for the topic, we need to rebalance. If we have new topics, you can subscribe to a regular expression, which means that if someone created a new topic that matches your regular expression, we also need to rebalance. So we have all those different scenarios. Of course, if someone new joins, we also need to rebalance in order to assign him some work. So all those things trigger a rebalance. You already know that rebalance takes time. And by default, during a rebalance, consumers don't actually do anything. Now, they don't have to not do anything. It's recommended that they don't do anything. But in theory, if you know that you have a sticky assignment, you can actually continue fetching while you're getting reassigned. We are now working, and you can see a proposal in the Kafka community by a guy named Konstantin. It's something called incremental assignment that will basically eliminate the whole. We're rebalancing, everyone stop doing anything at all, wait for a new assignment and continue from there. We're going to continue doing your work while things are getting reassigned, and we'll reassign things kind of one by one basis. I haven't read the proposal, to be honest, so I don't know exactly how will it be done. But I am looking forward to the results, because the stop the world part is really, really problematic when you do stream processing, and if you have large consumer groups, it can actually take quite a while, because it takes a while for everyone to join and the timeouts, etc. Okay, so suppose that we need to rebalance. How do I know as a consumer that I need to stop everything and get a new assignment? It happens in multiple ways. Sometimes I send a heartbeat, and instead of getting an okay, the coordinator will tell me, you actually need to stop everything and rejoin the group and do the join group and sync group and all that all over again. But heartbeats only happen like every 3-4 seconds. If I commit offsets more frequently than that, I can also get rebalance in progress as a result of a commit, an attempt to commit my offsets. And then again, stop everything, rejoin the group. And I can also initiate a rebalance. I can, as a consumer, may see that, hey, the topic I'm reading from changed, and we need to reassign stuff. So I'm rejoining the group, and then everyone else will also have to rejoin. It's kind of like a fake restart of sorts. And then when we rebalance, we have to stop everything we're doing, do not commit, do not pass a go, etc., rejoin and sync. Okay, all of this is basically implementation of an interface called the abstract coordinator. If you look at the Apache Kafka source base, this is what the abstract coordinator looks like. And if you want to override the protocol and implement your own resource assignment protocol, this is basically what you override. You override your definition for metadata, what is the resource, what is the thing we're subscribing to, and you override the way leaders perform assignment. So think about it, you can implement your very own generic resource assignment protocol by implementing two methods. And this is why I think it's a much nicer way to do things than use Zookeeper. Now, you may notice here that it doesn't say public. And that's kind of suspicious because I'm just telling you to override things that don't say public. So yes, it is kind of risky. This is not a public Apache Kafka interface, which means that the Apache Kafka community reserves the right to change the hell out of it anytime we want. In reality, it has not changed in the last 3 years, and we have a bunch of code that kind of relies on it not changing anytime soon. So I feel it's quite safe to suggest using it, but yeah, kind of do it at your own risk. Next. So I want to go through how do we do leader election using, yeah.
I understand the protocol that you mentioned. So is there any reason to, let's say I want to do a deployment which requires a restart for all of the consumers? Does it make any sense to restart the leader of the group last? I mean, the fact that I restarted the leader, does it cost more?
Not really. So the question is, does it cost more to restart the leader? The answer is no. Restarting any of them basically triggers the whole, let's wait for everyone to join the group again.
Another leader.
Yes, but choosing the leader is not a more expensive part of the protocol. It will basically, everyone will still do join group once someone leaves. So there will still be a leader election no matter who you killed. So this is not going to be that much of a big deal. I am thinking that the best thing you can do is make sure that you do the entire group restart before the timeout of the join group. So basically, once the join group, the first consumer rejoins the group and triggers the election, you have few seconds, I think it's like 5 seconds or something, that we're still waiting for others to join before we send back an assignment. And if you join in that timeout, you only do one rebalance. If you don't join within that timeout, you will have multiple of them. So even changing the timeout in order to do the rolling restart may be a good idea. I talk about it a bit more in depth. We have a Kafka Summit talk about, the best place to listen. Ask Confluent on YouTube. I interviewed Matthias Sachs, and he's from the Kafka Streams group, and he has a good explanation on how to do a rolling restart correctly in order to minimize the number of rebalances, basically. If you're not careful, you'll end up with two, one when you leave the group and one when you join it again. If you actually crash on purpose and don't send the leave group, you can end up with just a single rebalance if you do everything fast enough. So that's worth listening to. Yes?
You have some kind of service protection if one consumer is too often leave and join? Because every time you have the 5 seconds time on something like this, but every time it triggers a full cycle for all.
Yeah. And actually, garbage collection can actually make consumers lose heartbeats, and that can be an issue. We don't have any protection against someone flapping in and out, which can be, basically it can bring an entire group into a halt. I would consider using almost access control lists. Kafka has access control lists, so if you have any security enabled, you can say which privileges each consumer has, and they can be things. Joining a group is a privilege. We're worried about bad actors joining a group and kind of stealing partitions. You can use that to kind of blacklist bad consumers. So I would look into doing that. If you want something smarter, like auto-detecting when it happens, make a proposal to Kafka. It will be amazing. We all suffer very much from that problem.
And how can I identify in such a case problematic when you do all the rejoining?
And you'll need to keep history, basically. Right now, the coordinator does not keep any history of who joins and how often they join. We don't even keep identity right now. We don't know it's the same consumer rejoining. So it will require some sort of how to maintain identity in the protocol and how to keep history. Okay, leader election using the protocol. By the way, if you don't want to hear about other uses for the protocol and want to continue talking about consumers, we can totally do that too. How are you on time, by the way? I kind of keep talking and talking. I've been talking to 15 minutes now.
We have another 15 minutes.
15?
15, 20.
Okay, let's go through leader election and then maybe I'll finish it there unless someone is especially excited about either streams or connect. Okay. Electing a leader. Basically, schema registry is a way to add metadata to Kafka. It's a web service that allows you to do things like register a schema, and then we store the schema in Kafka, and you can say do get schema, and it's kind of useful. A lot of us have structured data in Kafka, and we find it nice. I feel like having just one schema registry is good enough. I mean, you only use it when you have new schemas or when a new service starts, so if it's down, it's not a big deal. Just use something like Kubernetes to start a new one. A lot of my customers, on the other hand, pretty much insist that everything they run needs to have high availability. And it's super, super important for them. So we added high availability mode to the schema registry, which is basically leader follower. We have one of the schema registry instances, it's a web service. One of the instances will be the leader. And it will get all the new schemas, and you can read from it. The follower, you can read from it, so if you want to get a schema, you can use it, but we don't allow you to write a schema. We only allow you to write to the leader in order to maintain consistency. That's all there is to it. So we are starting 3 schema registry servers. How do we know which one is the leader, right? So next. We are going to use the protocol. So we're joining a group. But now we're no longer joining a consumer group, we're joining a schema registry group. And because the resource that we are assigning is not partitions, the resource we're assigning is who is the leader. That's what makes it a leader election. So everyone basically sends in kind of which version of the protocol you're using, which is 0, and more importantly, it sends their own identity. They basically all register as candidates to become a leader. They say, and the identity is basically the URL that they're listening to. So I'm on this IP, this port, this is my identity. So everyone kind of sends host port pairs. And first thing that the coordinator does is elect a leader, right? So we send the leader a list of all the candidate schema registries, and then the rest of them get IDs, etc. And they know who is the leader. Next. Now those are my cats, by the way, Leah and Luke. So we elected the leader, right? We have a leader for the consumer group. Is that enough? And the answer is that it's not quite enough for 2 reasons. The first is that, remember, this is a leader that was kind of elected automatically by the coordinator, but one of our principles was that the clients are the ones who elect a leader. So we need to do something about that. We still need the leader. Basically, we need the leader to elect the leader. But the deeper reason is that not every schema registry candidate is eligible to become a leader. You can have schema registries that are installed in a remote data center, and you don't want them to become leaders unless you actually trigger a DR failover kind of scenario. So you can actually say those specific schema registers cannot become a leader. Please elect a leader from the ones in this data center. So you only have a limited list of schema registers that could become a leader. Next. But then the next time we do this in group, the group leader, it's no longer a consumer group, I guess. It's a schema registry group leader, elects a schema registry leader who may or may not be the same server. And the way we tell everyone who is the leader is that we send the identity, remember, host and port of the leader to everyone, which means that everyone gets the host and port of the leader. They compare it to their own, and then they find out if they're the leader or not. If they're the leader, they accept rights. If they're not the leaders, well, they have the host and port of the leader, which means that if I try to write to someone who is not the leader, they can actually do an HTTP redirect and send me to the correct leader. So it actually ends up being a pretty smooth process for the users because everyone knows who is the leader and can do a redirect. And again, if you look into the implementation, if you open up Confluent, GitHub, Confluent Inc., schema registry, and look at the way we implemented the abstract coordinator protocol, you'll see that the metadata is like a single line, host and port, and the perform assignment is about 2 lines. It's a look at all the host port names that are eligible to become leaders, pick the first one, send it, and just send it as a response. So it's incredibly minimal amount of code that implements leader election. Obviously, in your own application, you can have much more interesting leader election logic, and you can put whatever you want in there. But I find it pretty cool that you can do leader election in about 4 to 5 lines of code by just over everything else about who is in the group and maintaining membership and the heartbeats and all that is already implemented for you by Apache Kafka. So you get quite a lot out of the box. I'm kind of getting tired and I have a feeling that maybe you are too. Do you want me to go into, I think the next thing is Kafka streams and then after that is connect. How many of you are interested in assignment on Kafka streams? Okay, we have a pretty good group. How many of you are interested in assignment in Kafka Connect? Okay, let's go on to Kafka streams and we'll see if we have energy after that for Connect. What? I feel like we're kind of running out of time. Okay, so as I mentioned earlier, the abstract coordinator that the schema registry uses is not an official part of the API. And when there is a lot of questions that you ask in Kafka streams, and basically you say, this is really silly, why did you do it that way? And they say, well, we wanted to use the official API. Even though we're part of Apache Kafka and we actually have quite a bit of influence about whether or not non-public APIs change, they still really wanted to make everything very official. And you'll see a lot of questions like, why is it that way? Well, because we wanted to use an official API. So this is another one of the cases. The Kafka streams team wanted to use an official API, unlike the schema registry team, unlike the Connect teams that had absolutely no issues using an internal API. So they chose to, basically private API allows you to invent your own idea of what is a resource, your own idea of what is a metadata. You kind of invent your own language for electing stuff. If you only use the public APIs, you are essentially still a consumer group. You always, one of the things that you will always assign is partitions, but you also have a lot of user data that you can use to, for figuring out how to assign partitions and what else to assign with the partitions. And you do it by basically overwriting the assigner and overriding the user data that arrives together with a list of topics that you're interested in. So I'm going to show you how to do it. The reason that we had to invent our very own assignment protocol for Kafka streams, and Kafka streams is basically, if you think about it, it's a bunch of consumers and producers, right? You consume data, you process it, you publish it. That's what stream processing is all about. There's not that much to it. Why did we still have to invent our very own assignment protocol? Next. Another next. Okay, the reason we had to do it is that we do stream-to-stream joins. And when you join a stream to a stream, you need to basically make sure that the partitions of the two streams that you are joining will end up handled by the same consumer in the group. So it has to be coordinated. And then joins and aggregates also require some state. So there's going to be stuff stored on disk in a RocksDB instance. And we have to make sure that you get the correct partitions assigned together to the same task with the same, on the server that has the right RocksDB. All of this basically has to go together so you can do joins. So you can see that events for Gwen and JSON from this topic and that topic basically end up together. So we need some extra logic. We need to know that partition 0 here and partition 0 here ends up in the same place. We need to know that it ends up on the server that has the RocksDB information for Gwen and JSON over here. So how do we do that? Next. Basically, we changed, as we said, we changed the protocol, the assignment algorithm to be the Kafka stream sticky algorithm. And then we overrode the metadata like hell. If you look at how the task assignment works, you'll see that the metadata includes the host IDs, the metadata about RocksDB instance on the host ID. Obviously, we have the entire selection of partitions. There is something called standby tasks, which sends them some information about standby tasks. It's just huge amount of metadata all sent together. Next. So, and you can see, and then the partition assigner does quite a bit. So first of all, it has to validate that all the topics that everyone is interested in have equal number of partitions. Otherwise, none of this will work. You have to, and then you have to create a partition grouping and make sure that partition 0 here and partition 0 there end up together. We create those tasks, and we assign tasks to the consumers. We assign the consumers to the hosts and taking all the existing state into account. This is actually basically incredibly complex, and I keep forgetting how it works unless I have to debug something. And so will you. So every time you debug, you have to load a bunch of state into memory. No, next, it's fine. So you can see that when you do a syn group and you get an assignment, you're not just assigned, oh, you read those partitions. It's, hey, you read those partitions, you're going to run the code in those tasks. You're also running some standby tasks, which I'll not talk about. You're getting assigned based on the host you're on, because we have the host to partition mapping. So you actually get a lot of information about what you're going to run when you start running. So you do way more than just consumer from partitions. You're actually running code based on the assignment and storing things in the local disk based on that. And next, I think that's pretty much it. We want to talk about Connect, or? Yes, okay. Let's go assign some Connect tasks, and then we're really done. Okay, so Kafka Connect is basically all about how do we get data from databases into Kafka or from Kafka into databases. I'm going to just talk about one side, because that's kind of the more interesting side, because if you notice, there are no consumers here. The Kafka Connect has tasks. The tasks are reading from a database. Those are not consumers. Those are JDBC connectors. Those are connections to S3, to HDFS, to a Bloomberg terminal, to Netcat, whatever. And those are producers. So you basically have the things that we assign is not consumers to partitions to consumers. We assign tasks to workers. That's the resource that we're assigning. Next. And the way that it works, you can see again, it's a different protocol. We now use the Connect protocol, not the consumer protocol. And the metadata is basically, I'm joining the group. Here is the number of tasks that I'm allowed to run. I have that much capacity on the machine. That's what I'm allowed to run. Here is a list of task configurations. Things like the database address and the list of tables that I need to read and the username and password, etc., etc. And target state, which one of those tasks are actually supposed to run, because sometimes there are tasks that are really not supposed to run at all. And every worker that connects to the group has this list of configurations that he wants to run and the number of tasks that he's allowed to run. Again, elect a leader, etc. You already get it, right? We elect a leader. Leader gets all the members, all the metadata. Everyone else just knows what's their identity and who is the leader. Next. And then the leader basically sends a group assignment that includes two things. First of all, we decided that the leader that is elected by the group protocol is actually the leader for the workers. Why do we need the leader for the workers? Because you're going to have an HTTP port that you're going to use to stop and start tasks, to create new tasks. All those things have to happen through the leader. Again, now everyone knows who is the leader and can redirect HTTP requests to the leader. In addition, we are assigning tasks. And the way we assign tasks, the protocol is quite simple. We do a round robin, but we have two classes of tasks. Some tasks are get data from a database, which are kind of a lot of work, require usually a lot of memory, large buffers. But there's also tasks that just monitor the database. Did anyone create a new table? Is the database still up? That kind of thing. Those are very lightweight tasks. And suppose that we have kind of an equal number of each, and we do round robin, we can basically end up with one worker that does all the work and another worker that does basically nothing. So we do round robin for each class of tasks independently. Create an assignment, send it back. The leader is still the leader. We basically, whatever the coordinator chose, we are keeping. We didn't do anything smart there. And that's pretty much it for task assignment. And again, we did that by overwriting the abstract coordinator. What is metadata? What is the resource? Because that's the metadata. And what is the assignment algorithm, which is the double round robin thingy. And again, that's it. If you look into how Connect does it, we're talking about maybe 20 lines of code, pretty straightforward. Everything else about Connect, reading the configuration, is crazy complicated. This part is actually fairly straightforward. Okay, summary. Kafka has an awesome coordination protocol that you can, by the way, my first version has absurdly coordinated generic and ridiculously generic. My development team insisted that it's awesomely generic. Anyway, it's very, very generic. It's way more generic than we actually needed for if it was just consumers. It allowed us to use it for a lot more. You can figure out your awesome and amazing ways of assigning partitions. I don't think Kafka is optimal by any stretch of imagination, so you can improve things. You can also assign a lot of extra metadata. If you know something about your consumers that we don't, if you know how much your machines can handle, if you have limits, a lot of your own logic can go into your own custom assignment algorithms. If you now use round robin and you have your own idea for an amazing assignment algorithm that uses custom logic, you can do a rolling upgrade to use the new one. And then you can also use the protocol to assign resources that have absolutely nothing to do with Kafka whatsoever. And next, I think that's the last one. If you do implement your own coordinator, if you override our private APIs, please let us know. Just write to the Kafka user or Kafka developer list of Apache Kafka. It's super important to let us know for two reasons. One, so we can give you advice and kind of be happy that people use our awesome work. And two, if someone else is using it that is not Apache Kafka and not Confluent, we need to know so we can actually make the interface public and make sure that nobody accidentally screws it up for you. So if nobody uses it, we have absolutely no pressure to make it public whatsoever. So let us know so we can actually start the process of making this API public. Next. And then a bit of our future plans. As I mentioned, we kind of have a generation ID that could be used for fencing, basically protecting consumer groups from someone who joined late and is mismatched with the rest. We don't actually use it yet, but we should. Then the clients can basically control what they do while rebalancing progress. Right now they do nothing, but they can be a lot smarter about it. And then the fact that we rebalance everything every single time, even if someone changed and we can really do something way more minimal, we can really improve things. And this one is already in progress. Those two are really up for grabs if someone is interested. Next, references. See, if you're interested in even more crazy details than what I just mentioned, really good talk about offset management. This is the first redesign, the things that we didn't do, where the brokers did all the work and the clients didn't. This is the actual protocol as it has been implemented. If you want to override things, this is required reading, obviously. And this is the schema registry example, as if you want to implement your own leader election. And that's it. Now I'm really, really done.